Welcome back to BE 110. Today we're going to look at some properties of the Lagrangian and Eulerian finite strain tensors that we derived last time, and from that derive another strain tensor that's actually the one that's more commonly used in most engineering applications. But first let's demonstrate that, as we said last time, the Lagrangian green strain and the Eulerian Almanzi strain are respectively Lagrangian and Eulerian measures of squared length change with respect to undeformed squared length. The square comes about from the fact that we needed to take F transpose F or FF transpose to eliminate the rotation and be left with something that only depends on stretch. And you can think of this as being a consequence of Pythagoras' law. So we'll consider elements of length d little s in the deformed state and d big S in the undeformed state. So taking d big S first, by Pythagoras, d big S squared would be dx1 squared plus dx2 squared plus dx3 squared, or in vector notation dx dot dx, or in index notation dxr, which we could also write as dxr dxs times delta rs. And similarly, d little s squared will be d little x1 squared plus d little x2 squared plus d little x3 squared, which equals dxi dxi, or delta ij dxi dxj. Now, in order to collect terms, let's convert these elements d little xi, d little xj, using the chain rule of calculus, into d big Xr, d big Xs. So this expression becomes delta ij, del little xi, del big Xr, del little xj, del big Xs times d big Xr, d big Xs. And then, using the Kronecker delta to convert this j to an I, we get del xi, del xr, del xi, del xs times dxr, dxs. Therefore, the difference now between d little s squared and d big S squared will be del xi, del xr, del xi, del xs, minus delta rs, here, times d big Xr, d big Xs. Now, notice that dxi, dxr here is FIR. dxi, dxs here is FIS. In other words, this is F transpose, which is C, the right Cauchy-Green deformation tensor. So this term here is CRS, and CRS minus delta RS is 2 times ERS, the Lagrangian finite strain tensor. So we see here that this change in squared length is related to the elements of our original undeformed coordinates by the Lagrangian green strain tensor. So this goes to show that what the Lagrangian green strain tensor does is express squared length changes with respect to undeformed coordinates. Similarly, we could do the same thing, but this time we're going to convert d big S squared so that it will be with respect to elements d little xi and d little xj. So again, we'll use, this time, the chain rule gives us del xr, del xi, del big Xs, del little xj, times d little xi, d little xj, delta rs, which is del big Xr, del xi, del big Xr, del xj, times dxi, dxj. You'll notice that these are actually the inverse of the components of the deformation gradient. So again, taking the squared length changes, d little s squared minus d big S squared, we this time would get delta ij minus del big Xr, del little xi, del big Xr, del little xj, dxi, dxj. And this time we notice that del xr del xi is the inverse of FIR, del xr del xj is the inverse of FJR, and their product is the inverse of the left Cauchy-Green deformation tensor bij. So now we get that the difference in the squared length changes is equal to 2 times a to ij, since this expression is 2 times the Almancy-Eulerian strain tensor. So we can see that the strain tensors, the finite strain tensors, relate squared length change to either the current deformed coordinates or the original undeformed coordinates. Now let's derive the infinitesimal Cauchy strain tensor, which it's important to understand is actually an approximation. It's a linearization of our finite strain tensors, which are quadratic, and as such only is accurate under certain conditions. So to show what those conditions are, let's first expand the finite strain tensors in terms of the displacement gradients del ui del xr instead of the deformation gradients del xi del xr. So remember, the displacement gradients are just the deformation gradients minus I, or del ui del xr plus delta ir is del xi del xr. So therefore, the Lagrangian green strain components, ERS, which are 1/2 del xi del xr del xi del ss minus delta rs, these terms will expand to give 1/2 of del ui del xr plus delta ir times del ui del xs plus delta rs minus delta rs. And expanding this out, we get del ui del xr times delta rs plus del ui del xs times delta ir plus the quadratic term del ui del xr times del ui del xs plus the product del delta ir times delta is minus delta rs. And you can see that delta ir delta is delta rs, so these terms cancel, which leaves us with these three terms, and del ui del xr times delta is del us del xr. This term becomes del ur del xr, and the product is del ui del xr del ui del xs. So in the limit of infinitesimal displacement gradients, resulting in infinitesimal strains and infinitesimal rotations, i.e. when del ui del xr is much less than 1, so that this product is much less than these terms, then we get that in the limit, when this term, this second order term, is quadratically small, the Lagrangian finite strain tensor tends to 1/2 del us del xr plus del ur del xs, which is linear, and these are the components of the linear infinitesimal Cauchy strain. Now we can do the same derivation, starting instead with the Almancy strain. Now we get 1/2 of delta ij minus del xr del xi times del xr del xj. Expanding now again in terms of the displacement gradients. These expand out to, so these are the inverse of the deformation gradients, and so you can derive easily that they're equivalent to delta ir minus del ur del xi, and this term will be delta jr minus del ur del xj. Again, we multiply this out, we get delta ij minus delta ir times del ur del xj plus delta jr del ur del xi minus the quadratic term del ur del xi del ur del xj. Notice this time the sum is over the undeformed coordinate index, minus the product delta IR, delta JR, which again is delta IJ, which cancels with the delta IJ here, leaving us with the three terms. Del UR del XJ becomes del UI del XJ, del UR del XI becomes del UJ del XI, minus del UR del XI del UR del XJ. Again, in the limit when the displacement gradients are very small, this term is quadratically small, and the Almansi strain tensor tends to del UI del XJ plus del UJ del XI, which is again the Cauchy infinitesimal strain tensor. Now, if we look at these two expressions that we derived, you can see that the equations are the same, though the indices and the coordinates to which they're referred are different. In the limit, when the displacement gradients are small, the difference between the deformed and undeformed coordinates becomes negligible, and therefore, in the same limit, when these equations apply, the dxr and d big XR and del little x tend to come together. So these in fact are the same equation in that linear limit, and we normally write it this way in terms of current coordinates. So epsilon ij was 1/2 del ui del xj plus del uj del xi is clearly symmetric. It's the Cauchy strain tensor. It's linear, and it's valid when both the strains and rotations are infinitesimally or vanishingly small. It's not sufficient just that the length changes can be small, because this is an approximation, it doesn't exactly and properly eliminate any rotation. As long as the rotation is small, then the displacement gradient will be much less than 1, and this expression will work. But even if the length changes were small, but the rotations were large, then the Cauchy strain could be erroneous, because it would incorrectly reflect rotations as though they were a length change. So the Cauchy strain tensor in practice is very useful if the strains and the rotations, in other words, if the displacement gradients, which contain both length changes and rotations, are on the order of 1% or less. 1% is 0.01, 0.01 squared is 0.04, so compared to terms here of order 0.01, an adjustment of order 10 to the minus 4 is acceptable. And in many engineering situations, strains and rotations of under 1% are common. So think of hard engineering materials, including some biological materials like bone or teeth, wood. Strains reaching of the order of 1% are close to or exceeding the failure strain. And so for normal working conditions of these type of materials, the infinitesimal strain tensor is useful and appropriate and makes the problem linear. But for many biomechanics applications, we also know that the strains can be much larger. Consider muscle or skin or your lungs as they inflate. All of them can change shape by far more than 1% under their normal working conditions, and therefore, under those conditions, the infinitesimal Cauchy strain tensor is not an accurate approximation, and hence we need to use the finite Lagrangian Green strain or Almansi Eulerian strain. We'll do some examples of these in the different strain tensors and deformations in class.